Hello. This video I recorded because last evening lecture at the end we don't have sufficient time to show you uh, how we can create a source program to put some kind of payload shellcode uh, inside the different section of a PG file. So before we can go into the demonstration, I need to do some housekeeping work. I need to install File Insight, and I need to put the reverse engineering demo, which I share in the Dropbox. Uh, I update one more item called debugging for fun as like the second part of the demonstration of today's video. First of all, let me okay, go to the temp folder and I drag the reversing demo folder from the download from the Dropbox links. Inside the reversing demo, you can find the Hello World demonstration source as well as the debugging for fun binary. Now, the second thing I need to do is try to install the File Insight. File Insight is in the supporting tool, I think, suppose. Yeah, File Insight. I need this to show you the location of the payload. So I minimize it. Now see whether this recording will be able to check more easily. So I go back to the malware development free development program right there. I go to resources and then sample malware development. Of course, we can do the expand the folder in this location. I find that payload storage. Now we try to implant the payload in data. So we find the source code and we check the source code with Notepad++. You will see that that is a simple payload right here, which is not inside the main. If this section of code put inside the main, uh, you will find this in .text section, which is code section. Now, if the payload has been declared as a variable with four byte instruction, doing nothing, just stop there and then return. So the payload will be called inside the main program. The main program will create a new buffer and then change the and then we move the payload to the buffer, and then we change the newly created buffer memory permission by adding its as executable, and then it shows the payload right there. So what we are going to do is to first we compile the program. Let me try to compile the program. Maybe we can try to compile program as 86. Let me try see whether we can work for that. And then we change this compile batch file. See if I can make it work with 86 instead of 634. Or 86 means the 32-bit environment. Let me change. I don't want to do this and close it. So, and actually the object file is created previous compilation tool. So I delete it. Now I go to the Visual Studio and I find 86 native tool. Yeah. Uh, my folder to the program location, see if compile works. Okay, cool. It works. It is a 32-bit the program. And now let me do one thing first. I check whether it is uh, whether this section, the data source data, 4 byte data is 9090CCC3 lies in the data section. So I use the file inside, just installed previously, and then load that program, newly compiled program called implant under the malware department, payload storage in the payload data, this one. So in File Insight, I have a hexi editor. I can check each hexadecimal data in each section. For example, this is text section, which is the book section, our data, and the data. You see 9090CCC3, which is inside the data section. So the payload should be at the address of whatever 1800 and raw, but in the virtual will be different. So I minimize this and then see how I run the program. So let me try to run the program without anything turn on, but I turn on the process hacker. The process hacker right here, and I don't like the FP. You don't need to do the same thing as what I'm doing. File Insight, turn on. I have the command prompt right here. I have my address. I can check the address right here. Okay, so let me try to run the command prompt with the implant.exe. It come out the payload address and then executable memory address. Okay, so payload is E3A00 in the memory. Now let me check. Maybe every time when you run this, may be different because the randomization of memory function has been kick start. Let me check with see whether I can find the permission in the payload E3A00. You're sorting. Okay, maybe this one is not correct. I'm trying to check with the implant. Yeah, implant is only 32-bit. E3. I don't see the E3 A00, E3A0, E3A00. I don't see this at this moment. How about I try to find DF? It must be created already. Yeah, this is the buffer. Read write, and it marked it as executable, right? As private already by the program. So let me to hit me one time, and then it finish. Okay, I can't see anything dynamically without the debugger. Now let me try to using the debugger. Drag this exe to the x32dbg. Now I go to the user code. I stop at the entry point. Every time you load up, map this image to virtual and let it run, the base image will be changed. So see what I can do. Let me try to, I remember that its source code have two major parts that may come to our interest. First of all, we can do the tricks to find where is the interesting location in the payload address and memory address And then by using the magic in the demo is hit the key to find where is the address we need to pay attention. Another is we check the API call, virtual protect, and virtual hello. So first of all, we create two big prompt. Before that, we check there's no big prompt right here. Big prompt, virtual hello, big prompt, virtual protect. So check the big prompt. We have two new, we create the big prompt. So before we do the debugging, how about we do a checking on the IDA post? We have the start, but we don't have the main. How to find the main using the tricks that go to the wheel, open sub wheel, find the strings wheel. It doesn't come out. What happened? Okay, try again. Go to subview strings. Yeah. Now I do a search heat. I search the keyword heat. If I double click right here and I find the blinking right here with the highlighted blue in this data location, but this is only data. Hit me, we can find here. I want to go to the block mode or the IDA block graphic mode. So I double click here, it automatically provides the information right here. So I see the virtual hello, virtual protect because it's the symbol that have been recognized by the IDA pool. So I have different function. You must be remember that we have the in the source code we have the um, somehow pre-nav and show the hit me and the printf to show the payload address, executable memory address. Now, let me rename it as the main. We type the N, and then rename it as main. And then try to find the function called printf. We don't have the signature to identify the function of printf. We got it at the disassembler. IDAPO, we got it as some kind of shell payload or just like a shell code. You don't have the API identified automatically. But from a while guess pushing to this parameter to the stack, and then you will be able to see it make a call. And the calling address is 4010C0 or RVA1C0. If I click this, you will see three items have been identified similar to the source code PNAP, three PNAP, and then one get character. Now we can rename it as printf, then I type N, and then 1, 2, and 3. And before that, we have another one is get character. printf hit me and then get character. Hit me here, and then print F, and then get character. I think this one is get character. Okay, I type N. This part is not so important for our main purpose, but I want to also show you how I can use the IDA pool to make it more easy to understand without the compiling the code by using the F5 function. Now, come to our interest, we need to find the virtual arrow and try to find the buffer created. And then I want to observe how these um, memory from the payload in the uh, mapped location to copy to the newly created buffer. And then at the later section, it will create a flag. If you want to pay attention when this calculator create, then you find the create flag and then hit spacebar. You remember the RVA 1091. Then we can easily observe how the calculator, how the payload is executed. The payload is 9090 CC and 31. Okay, let me go to the debugger right now. So first of all, I am right now in the entry point. Let me hit run to stop at the virtual arrow. Hit run. This is run. F9. I hit the virtual arrow. Okay, so the newly created buffer is random. In the heap is E3AE58. Then let me right click, go to the dump1. Don't worry, you get some garbage right here because we just stop here. It is not the final one. So how about we go run until return? Maybe this is not the location of the new buffer created. Then I go to hit until return. Now we have a new EAX register return value. This is the true buffer that has been newly created. You see everything is empty, right? Okay, so I just go inside this jump to step over, we return to the calling function. This is the code section. If you click one back step, you will see the virtual arrow have been called in the data section. The code is not actually called directly called the API name, a function name called virtual arrow. Instead, it just called a data segment. You still remember that the E flag CPU register one of these data segment the segment index is called the location right here. So you will see that if we step over one item by one item, you will see push, and then make a call. You will see push the payload address. See whether we can see the payload address right here. Yeah, we have E3A000. So if we want to find this address, this location, I copy this and then open a dump2, Control G to go to location. You will find this the payload. The payload is 9090CCC3. That is the location. And then dump1 is not updated with this payload. So we step over, stop effort, step over. We just show the information and print out as the memory address. The new address is 10B0000. So everything looks okay. Now, can I observe how the payload has been moved? Then you pay attention right here, and I don't know which functions do the move. Yeah, it obviously at the address RV1052 do the move, and the move is this 4 byte move to dump2 to dump1. We can clearly observe this. Now, can we check the dump2? What is the dump2 permission? What is the dump1 permission in the memory? So now I go to the imply under the 32-bit environment, and then here we try to find dump2 address is E3A00, E3A00, E3A00. Yeah, right here. Can I see the text? Yes. If I double click, I can find it. Hexadecimal character 9090CCC3, same as the dump2. Now, can I see the newly created buffer E3A00, E3A00? That is read-write permission. Yes, it is not executable yet. I find 9090CCC3. So everything looks good. Now let us go to the run again. Now I go to the virtual protect, and then it is only start at the location of virtual protect, but I need to hit the virtual protect to be executed until return. And then I go to step one more step, go back to the source with the code section. This is, if I move back a little bit, you'll see the virtual protect under the data segment. Now, can I double check the EA, double check the newly created buffer permission? Now I go to the imply E3 something. It is still the read write. See whether something can change later on. Let me double check again. Still read write. Now see whether I can make a call. Oh, I need to hit me. Then I hit. Now, if I check this again, E3, still read write, not executable. Unsurprising, it should be changed to executable. Now, before the create thread, see whether I can see some other thing changes. E3A00, E3A00, still read write. Now, let's go to create thread. It didn't change. I wonder. Maybe we need wait until to wait for single object API. Read write, still read write. Right. Let's go to see some more step. Now we stop here. The dump location is at the 1B something. How come it changed to 110B0? It must be some other thing changes. For example, E3 still right here, but if we go to check the 10B, oh, still that is E3A00, E3A00. Oh, I mixed up totally. Actually, the dump2 is the payload location. The newly created buffer is 10B00. Oh, I mixed up. That happens a lot. 10B00, and you will find it changed to read execute. I mixed up, spend a lot of dummy time. Now, if I click one more, you will see it goes to the thread has been created, I think. Now it terminates. Okay, so this is not a too good demonstration, but I my intention is to show you how we can use the virtual allo and virtual protect and create a breakpoint on these two API call, and then we can dump the buffer and check and monitor how these API call manipulating the memory enable the memory to be executable, and then let the um, payload or shellcode to be executed in the newly created buffer. Uh, Let me take a small break and then we play with the sample called debugger for fun. Okay, we are not doing anything on the incline resources. But basically, I need to explain this before we go to the uh, binary that I compiled called debugger for fun. Basically, it is the same function in the payload store in the resources section. As you may remember in the lecture, I told you guys the resources section basically it keeps the menu and icon and some other information in the PE file. But actually, a lot of malware often put the payload encrypted and put inside the resources section. When it execute, it try to they try first create a buffer in the process, and then extract the payload in the resources section, and then decrypt it with some kind of way, usually exclusive or with one key or a sequence of rotating key, just like transposition encryption, and then byte by byte and using exclusive or to change it, and then move it to the newly created buffer and calling the virtual protect to make it as executable and pass the instruction to that to kickstart the payload. The resources in incline program inside here, the basic concept is like that. But except this version, we don't have the encryption key. Let me show you the source code similar to the things that we are going to do. First of all, create the different kind of initialized variable and declare a buffer called payload by calling the virtual arrow, and then we need to extract and read the payload from the resources section. Here we are using a standard simple payload to kickstart a calculator, and then yeah, and then we can have the print out the payload address just like the instruction implying that we show in the payload inside the data section, and then print out the newly created buffer location, and then hit me and start create a thread, and then wait as for single object to create the calculator. So that is the logic right here. Then we go to the temp folder. Uh, Inside the temp folder, we have one binary called exclusive or calculator. So let me copy this to the temp folder for easy manipulation. Password infected. First, let me run this. It shows the payload address. It's the newly created buffer, and then hit me to decrypt, and then copy the buffer. Yeah, a calculator can come out, and you will see that in the process hacker, you will find different kind of things. You will find the new calculator, and you don't see the exclusive or calculator process anymore. If I close it, I close it. Okay, let me shut down the file inside. I don't need the IDEA pool again because I will call using IDEA pool to find this function. So first of all, let us do some checking. Suppose you can go to the resources section to find the shell code, but I don't want to do this because if it's more complicated, I want you to see it in the uh, debugger. So let's first go to the IDA code to do a preliminary study. Still, I don't know where is the main program, but how about we use our magic for this example, go to subview to find the string and then do a search for the heat. Yes. Click here, you will be redirected to the data section. From here, whenever you see the blue things, you can click into block location. Only this is, oops, sorry. Now we are, what are this forgetting? We are in the main program. Change it into main. Same as the previous one, we can down here, we can see some other thing. Here you will see something move. You remember last evening we talked about the instruction code, one instruction code called LEA, which is a more efficient way to execute the command called move. We are using LEA. It moves some variable to the EAX register to use, and then I guess this is the payload location. So if I want to remember this, I try to go to the list mode and find the RV1226. Remember that. You remember that. This is the LEA instruction. We'll push the LEA from this variable to the EA register to the stack, and then also push the calculator something here into the stack and then make a call. We don't have the same. We don't have the PINF being identified by ID pool, but there's free PINF free statement, free string in the screen. Suppose I can rename this as PINF. And then after the PINF, you will be able to identify the get character. Now, we need to see something. We need to see what happened here. We have a loop right here, and inside the loop, you will see the EDX, ECX register, and then you will see the LEA moving something right here. This another move variable to the ECX register, not EAX, because EAX we want to push it into the stack usually, and then make a call by the calling convention. But the ECX is some kind of index copying something, move something, like or compare something. So you see the compare right here with with different kind of compare with E6, E8 register, and then we do the exclusive for. I wonder this is the key have been used to decrypt the resources information. So remember this 126B, or anyway, Here we are assuming the calling function. This is the location we need to pay attention with. Um, then maybe we can somehow step over to find the encryption key, especially in this moving LEA thing right here. Okay, so we have the basic idea, and then we'll see the virtual protect, and then it will call create thread, just like the um, payload in data demonstration last demonstration. So I minimize this, and now we play with the debugger. This is what I call debugger for fun. First of all, I need to create two buffer. Call this optional header. Forget this. I don't need to take care. I create breakpoint virtual arrow point. So, okay. These two buffer two things created, and then let me go to the user code. Right now, I am in anti-error.dll. That is the entry point 15E3. Then see whether I can go to the main. I don't know where's the main, but because the IDA will give me some hints about this. Is 1040 1040. I go to the Control G to go RVA 1040. Green color, I'm good. I want to stop here also. So let me go to run. I stop at the main. Then I don't want to see these other things. Is quite clumsy. So I go to run again. Let me stop at the location of virtual arrow. I stop at the virtual arrow. As usual, the buffer has not been created yet until I go to the run until return. And then I step there, return. When I check the EAX register, I do the dump one. Newly buffer created, nothing right here. So where is the payload? The payload supposed at the LVA of, I think I cannot remember, but suppose it's supposed at the address of the LEA right here is 1226. 1226. Now, can I find 1226 right here? 1226 right here. Okay, so we see the instruction code is moving EAX register to EDI. It moved to EDI. This is the newly addressed move to EDI, ED index 1F000. Now we are moving something to the EAX register. So what is the ESP plus 8 or whatever? So we see 4496 something. So I don't know, but we can wait until we step over and check the EAX register. 96FAD0. Okay, now let me do the dump in the dump window too. See whether we can find anything. Now you can see a bunch of the stuff right here. Nothing you can recognize until you find something. I find some interesting human understandable thing right here called ugly gorilla 4 Hong Kong U 7905A. Yes, I find something interesting right here, but that is my intention when I create a key, transposition key for converting exclusive OR from decrypting the encrypted payload. So I intend to create a meaningful human readable encryption key for you to identify. But then still, we do have something. If we don't have this, how can we identify the key? It must be in somehow, some location, but this is not the right moment to find it. So let me go to step over again. Now you see dump one. Now you see that is a call right here. It puts everything into here. So this call, basically 1370, you still remember that is PNF 1370. So everything right here is just print out the stuff. So I don't need to take care until I finish these two exclusive or these two exclusives or just clean up the stuff and including this one. So I just step over until the DEX exclusive all. So I don't need to take care of this. I just click, and then you see the payload address is 96FAD0. Dump one. Sorry, dump two. Yeah, that is the dump location. That is encrypted payload. So let me step, and then print a other information is the newly created buffer. The newly created buffer is 1F something. 1F something. Now let me check what is 1F000. Now I click this 1F00 is read write, not read execute. Now let me run, and then print the message, hit me to decrypt and copy to buffer. So I click one, and then hit me, do the hit me right here. It doesn't respond because it's still waiting to execute to get character. So I step over again and I hit the space. Okay, it's not yet. Now how about we do something? Here we clean up this everything. Now we'll go back to the encrypted payload from the location. So we see ECX, EDX move. I have no idea what's this. And then now we see LEA, which is moving something in the variable to the ECX register. So if you have a good observation in the hints window, you already find the key ugly gorilla for Hong Kong U7905A. But if you miss, don't worry, check the ECX register later on. You'll find it right here. Okay, so that is the encryption key. The exclusive OR is the function to do the loop inside with the first character D in the encrypted payload. Try to compare with the ugly gorilla, the first character called U, EAX register in the lower byte 75, compare with the D character, and then try to do the exclusive OR and convert into some other things. You see D change into 1. Okay, so if I don't want to check this item by item, actually it will go to the loop and then it will loop it again according to the IDA poll instruction. If we go to here and they do the comparison, see whether it's finished, it will loop back again. I don't want to see the loop back. I just want to hit enter. Pay attention right here. If I go on the one, this section of code will be decrypted in the payload in the memory. But the dumb ones still have nothing because we have not moved everything to the dumb one. So we hit the run, and you see everything have been decoded, and the aggregate information still residing in the payload section, but the payload have been decrypted into to be runnable. The dumb one, oh, the dumb one already contained the decrypted payload. So we go to the virtual protect. Virtual protect is the 1F something. See where that 1F something we have been decrypted. 1F something is still read right. Oh, we just stop here. The virtual protect won't change until we go to the until return. Yes, read right, still read right. 1F something. Okay, anyway, go to the step over. Anything change 1F something. 1F something. 90, it should not be 90. But anyway, we see step something more. See whether they change. Oh, actually, it is not dynamically updated in the process hacker. When you check the content inside, you need to close and reopen again. Oh, another dumb thing. Actually, it changed the virtual protect been changed. If we keep on running, when we go to create thread, just like the example previously before, a thread has been created. If we click the create thread, maybe we can find a handle. Yeah, suppose. Let me go to the handle menu right here. Go to handle. I don't see a thread here. Okay, let me go to create a thread. Yeah, it dynamically creates a thread by using the process hacker and by checking the content in the kernel as well as the memory. You will be able to identify how the code injection, decryption, creating buffer, all of these things may affect for how we identify a stealthy activity of unaware. So not only 5 elements we need to consider other than these 4 standard process and thread, and then we need to consider the register, file, and the network activity. Last evening, we talked about the memory condition, the permission that we checked previously in these 2 examples. And now I find also the handle, which is an object inside the kernel, but reflected can be accessed by the user mode API by the programs such like the process hacker. We can find quite a lot of interesting things in the malware when it's executing. And then if we keep on running step by step, go to wait until object create, you will see the calculators come out and the command prompt has been terminated. So that is the major purpose of my demonstration today. And the second part explain everything we discussed about how the interaction of the PE file do the mapping to the virtual, and then the virtual arrow and virtual protect, extracting the resources encrypted payload and do the decryption uh, in the sample call debugger for fun using a transposition key by applying the key to each byte of the uh, encrypted payload and decode it and move to the newly created buffer, and then change the created buffer permission to read write execute or read execute, and then create a thread and wait for a single object, and then the new process running. So thank you for watching this long video.